Hello, everyone. Welcome to the first technical session hosted by Amoye in the Spring 24 cohorts. We are an EdTech startup committed to preparing young adults and university students for careers centered around data, tailored to meet the demands of the ever-changing job landscape. Hello, can we all hear me now? Sorry, apologies for that. I'm going
Yes, ma'am.
to, yeah, all
We can
right.
hear you.
All right, so welcome to the first technical session hosted by Amoye in the Spring 24 cohort. We are an ed startup committed to preparing young adults and university students for careers centered around data, tailored to meet the demands of the ever-changing job landscape. By simulating genuine work settings through hands-on internship, we bring together specialized coursework, informative webinars, and hands-on projects. We also expose you to industry-relevant project presentations like what we are having right now. My name is Mercy, and my job at Amoye is to make sure that you have a smooth experience. I'm joining you from Ibadan, Nigeria, and will be your host for today's session. I'd like to welcome to this event everyone present currently, our incredible interns in the current cohort. Kudos to you. And thank you for making it this far. Thanks to the Amoye Fellows and the Amoye teams who have made this session possible. And we are psyched to announce that today we have an Amoye Fellow with us, Jolomi Tosanwomi. He is a Amoye Fellow, graduate student, and a research assistant at the University of Toronto. He holds a degree in mechanical engineering from the University of Benin in Nigeria. He gained experience as a data scientist at QuickCheck, where he collaborated on developing machine learning models to score loan applications for both QuickCheck apps and Jumia Pay. Jeremy was a data analyst instructor at Utiva, where he taught post GRSC SQL for data analysis. He's also a former data scientist at Turing. Jeremy has a strong passion for working with data and excels in utilizing machine learning to address various organizational challenges. Outside of data science, he is interested in leadership and mentorship. He is currently the president of Black Graduate Students Association at the University of Toronto. And you would agree with me that that's quite a loaded CV. And today, he will be speaking about the topic social network analysis. We've seen that on all of the advertising e-flyers and all of that. However, before I hand over to Jolomi, please carefully take note of the following. Feel free to post your questions. It will be talking a lot about many interesting things and many useful things for us. So feel free to post your questions and comments on Slido using the event code 3241860. 3241860, and they will be promptly attended to. Now, to the business of the day. We told you all that this session is very, very important for all Amoye interns. And we are going to be taking attendance. Now, for last names, I want everybody to listen carefully to this. If your last name begins with the letter A and or between the alphabet A to M, if your last name falls within that, maybe your last name is Adeleke or I don't know, any other last name you may be bearing, between A and M, then you should fill the first attendance form that will be dropping right now. If your last name does not fall between A to M, please do not fill the attendance form right now. You fill it much later. You get the chance to fill your attendance form. But if your last name falls between the letters A to M, please fill the attendance form that will be dropping on the YouTube and on Zoom right now. Thank you so much. I hope we all got that. And over to you, Jolomi.
Okay, all right, yeah, thank you very much. Just to confirm, like, can you hear me? I don't know if anyone can confirm this. Um,
Yes, we can hear you.
okay, all right, thank you. Thank you, Messi, for like that intro, and it's my pleasure to be here. And so today I'll be talking about social network analysis, and I think I'll just dive in because of time, and we get started right away. So yeah, just give me a minute to share my screen. It's, I don't know if anyone can confirm if they can see my screen.
Yes, we can see your screen.
All right, thank you. All right, so I feel like the voice social network analysis is more like application based. So actually, it's actually there's a broader topic name called network analysis, and that's what I'll be talking about. So along the line, I will just kind of I will kind of focus on the use case, which is a social network analysis, but I'll just start from the high level, which is network analysis, and just talk about it and stuff like that. So yeah, so this slide is kind of like gotten from the open source Stanford CS224 course, right? And I think it's very, very useful. So I'm going to yeah. So what are networks and complex systems? I think I will start with complex system because there's a relationship between network and complex system. So complex systems are all around us. For example, the society is just a complex system. Yeah, currently the world population is 8 billion. I think this slide was created 2017. So yeah. So currently it's 8 billion people. So that's a very complex system because we have 8 billion people with some form of interactions between them, right? People are relatives to one another, or people are connected on some social media platform. We also have communication system as a complex system, for example, electronic devices. Then information and knowledge itself can also be thought of as a complex system, right? You know something that knows some other things that and stuff like that, right? Your knowledge is kind of chained together. And then we also have genes and proteins, right? DNA, they are all complex systems. You see these complex structures and interaction between them. So, I mean, complex system is just like around us, and we live in a complex system. Everything is a complex system. So the big question is, how can we represent complex system? Because they are complex, there's a need for us to represent them in a much more simpler way before we can understand them. So we're going to like dismantle the components of a complex system and see how we represent them and analyze. So, I mean, all of those examples I gave, you can all visualize them something like this. So this is called a network. So one way to visualize a complex system is a network, right? So network just, I will talk more about network, but just a first a teaser, just basically representing the entire complex system as is structure that contains interactions between different entities, right? For example, each dot here is an entity, then the lines connecting two dots is an interaction. So complex system, we have they are made up of entities and interactions, right? Interactions between entities. So network, we have like many network is behind many systems. So network is just the intricate wiring diagram that is behind a complex system, right? So we can study the network behind the system to understand that system. So then we look at networks and the application. For example, this is a network representation of people on Facebook as of 2011. So you see like each node, which is like a dot, here is a user of Facebook. Maybe that user is in Nigeria or US or Europe and stuff like that. So if they are friends on Facebook, we draw a line between both of them. And then you see that this is a like beautiful representation of the complex system of Facebook, for example. So this is just a nice way to view the interactions between people and the connectivity of people across the world. Also, like if you narrow that down to a sample individual, for example, if I were to plot the network of a sample user on Facebook, so let's say that user is user U, which we call the ego. So every other like user will be connected to that user because we are analyzing that user. So everybody is connected to that user basically. And if we look at the network of that user, we see some sub networks, right? So those sub networks have some like properties and interesting attributes. For example, we can see those family, like the family members of the sample user may be connected like within themselves, right? Similarly, the high school friends and the college friends and stuff like that. So we see this complex system inside another complex system, right? So it's a form of a nice way to detect the communities, right, within your network. Another complex system, for example, infrastructure, water supply can also be formulated as a complex system or a network. We have like pipes and water flowing through them to serve different houses and buildings. We have airlines, right, connecting two locations on the earth. And then we also have contact tracing. For example, someone moves from like Africa to America. So it is also a complex system, it's a movement, and then we can use it to form of analyze epidemic or pandemic to kind of trace or contacts and stuff like that. We can also use it for uh, basically online, like social media. We can basically plot the network of your followers on Twitter or X, sorry, X, and then maybe we have something like this, and then this is like, for example, on X, like we you can most likely find two broad communities, right? Basically, like contending among themselves, people with different ideas, maybe kind of a polarized network. Maybe Democrats and Republicans, those that believe in A and those that don't believe in B, just driving a trend or arguing about the particular trend basically. Then we can also represent transactions as a complex system, right? Some user A transfers money to user B and stuff like that. We can use it to trace the movement of money and maybe watch out for money laundering or detecting fraud. So all of these are like kind of the nice way. And this is an interesting complex system or network. It's called this Zachari's Karat Club, I think in the 90s. So there's this club in the US. So basically, Zachary like observed the interaction between members of the club, and then he plotted it as a network. So if team member one spends time on phone call or chatting with team member two is going to connect an edge between them, like a line would connect both of them. So you basically interview them to kind of ask for the person they speak to most of the time. And then he represented this as the network of the interactions amongst members of the club. And then he noticed two communities within that club, right? So these are the first communities who are just all around Mr. High, then another community is around the officer, which is like the CEO. So this is actually the coach of the club, while this is the CEO. And then Zachary predicted that this club is going to like dissociate into these two groups in the future, right? Because there's like why everything is going on, the fans are watching the club, they are playing, everybody's happy, but internally there are two communities that are being formed, right? And truly, after some years, the club really splitted across this line, right? People that buy the ideology of the coach went to the coach, and those that were with the ideology of the CEO went to the CEO. So it's just kind of a very like nice network analysis stuff there. So networks really matter, and it's very important we like pay attention to them, right, and stuff like that. So there are some terminologies you find out here. Some people call it network, some other people call it graph, but they basically like refer to the same thing. But just to try to put things in perspective and to be explicit, network, we say network often refers to rich systems. For example, the web, social network, metabolism network. All of these are real systems. While graph is a mathematical representation of a network, right? And then uh, we say a network consists of nodes. For example, let me just call it node now. Let me just call it entities. So a network consists of entities and the interactions between entities. So if I take this entity and that entity, if they have some kind of interaction between them, I'm going to connect them with a link, right? So for those that call it network, those entities are referred to node, while those that call it graph, which is a mathematical representation, those entities are referred to as vertices. Then the connection between entities, for those that call it network, they call that connection link. So here they say there's a link between node A and B, while those that call it graph, they call those link edge, right? But sometimes people use this interchangeably, but it doesn't matter so long it gets the idea, right? So sometimes you find me calling these nodes or maybe vertex, or you may find me calling this link or edge, right? But it's just the same idea basically. So I mean, if we start with this basis, we can use this building block to build a complex network and kind of analyze network. So let's dive in right now. So we have different types of network. Now, graph, if you like, they are still the same thing. So we have the undirected and directed graph to start with, right? So directed graph means there is a form of direction in the interaction, right? So there's a form of direction that should not be ignored in the edge. For example, if I call you, so if I am user A and you are user B, if I call you, the connection between me and you, we are going to like create an edge between me and you, but that edge would have a direction because I'm the one that initiated the call. The edge will be pointing from me to you, right? So that is a direction that we cannot ignore. For example, here you can see that user B has, for example, called user C, or user C have never called user B, but kind of so that's a directed graph, right? We also have undirected graph. There's basically no interaction between them. For example, friends on Facebook, if we are connections of Facebook, there's no form of direction we can associate with that. What matters is that we are connection, right? There is something connecting both of us, right? So basically, so there's no sense of direction. So that's undirected graph. And then we also have complete graph. A complete graph is basically a graph that is like that. Each node is connected to every other node. Like there's 100% connection. Like, although you can hardly find that in reality, but theoretically it exists, and we can. And the formula for calculating the maximum number of edges in a fully connected graph is n combination 2, basically. And then we have also bipartite graph. So bipartite graph is such that the entities in the graph or the nodes in the graph, there is some kind of exclusivity between them, right? There are some, we can think of those nodes as two, like a sense of entities. For example, all nodes that belong to the set U cannot belong to another set V, right? For example, if I cite, for example, if you create a network of authors and the papers, so there, if someone authors a paper, we create a connection between them. So authors and papers, like both of them are nodes, right? But then they mean two different things. An author is a human being, a paper is just a paper, right? Something out there, but we represent both of them as nodes. Then the connection between them is if and also participated in writing the particular paper. For example, if you look here, let's make this up. If you look at this paper, for example, it was written by both author B and C, right? But then why is it called bipartite, right? They are true that the nodes associated with this network, they are mutually exclusive, right? For example, papers cannot be authors. So we have things that are similar, which like authors in one side, then papers in another side. You don't have interconnection between paper because the paper cannot write another paper. Neither do we have interconnection between authors because author can write another. The connection is between, like, it cuts across the two groups. So this is bipartite graph. And you can actually fold this bipartite graph into something like this, which is the folded version, right? For example, you see this particular one here is connected by B and C. So you can create a connection between B and C because it participated in writing the same paper, D and F, D and E, and stuff like that. Yeah. Okay.
Hi,
So,
Jeremy.
yeah. Attendance?
All right.
Yeah.
So we want to use this opportunity for a pause in the explanation to tell the other ones with surnames starting from N to O or the rest of the surnames, whether your name surname is Z. This is the opportunity for you to fill in the form that will be dropping on Zoom and YouTube now. So you have 5 minutes to fill out the form. The link will be sent and the code, the secret code is Mistral, all lowercase. Please, Mistral, Mistral, all lowercase. Thank you so much, Julumi. You may continue.
Yeah. Thank you. So, again, back to the directed and undirected graph, right? So this is a directed graph and this is an undirected graph, right? So far, we have only thought of representing them as structure, maybe just some kind of diagrammatic representation of the network or graph. How can we represent it mathematically? There's something called the adjacency matrix, which is just basically a matrix. It's a squared matrix, which is like the number of rows is equal to the number of nodes in the graph. The number of columns is also equal to the number of nodes. So basically, if there's a connection between two nodes, we are going to give a value of 1 in that adjacency matrix. For example, there's a connection between node 1 and 2. So if this row refers to the first like node 1, node 2, node 3, node 4. Then this column is also for node 1, node 2, node 3, and node 4. So right here you see a connection between node 1 and 2. So that will be a row 1 and column 2. So you put a 1 there and so on, basically, right? So this is an adjacency matrix. For undirected graph, you notice that the values in the adjacency matrix are going to be ones if there's a connection between the two nodes and 0 if there's no connection. But for directed graph, uh, an adjacency matrix of a uh, undirected graph is kind of symmetric, right? Because if there's connection between 1 and 2, there's no sense of direction, but undirected graph is not symmetric. For example, node 2 is connected to 1, so in row 2, column 1, you see a 1 here, but row 1, column 2 would not have a 1 because 1 is not connected to 2. Like 1 is not, there's no edge that leaves from 1 and terminates in 2, basically. So most real world network are sparse. So sparsity means that if you take the average number of edges, right, it is way less than the average number of nodes, right? We have bunch of nodes compared to the number of edges. For example, the like if you look at LinkedIn connection, it has over 6 million nodes as of 2009, but the average number of edges is 8.87. So we have a lot of unconnectivity, right? Basically in a real world network and they are sparse. So that means that the adjacency matrix will be filled with a lot of zeros, right? Basically with a lot of zeros. And yeah. So what are the possible things we can do with edge, right? So far, we just see that edge can actually take the value of 1 or 0, right? For example, there's a connection between 2 and node 2 and node 1. So we just give it a value of 1 here. But what else can we do, right? We can actually, beyond giving everybody value of 1, we can actually give some kind of weight. For example, maybe the frequency of communication, for example, or we can do ranking and basically some attributes of the edge that makes the value not to be 1. Maybe the value can be 0 point something, right? Which is something like it's kind of a weighting system. And then we also look at more type of graphs. So that means we have the unweighted and weighted graph. So basically, unweighted graph, the values in the adjacency matrix are either 1 or 0, but weighted graph can be any real number, basically, any positive real number, right? Calculated from some kind of a weighting system. And then we also look at self edges. For example, a node can also connect with itself, right? In some cases. And then we can also have things like multi-graph, right? For example, there can be multiple nodes connecting, like um to there can be multiple edges connecting two nodes, right? And in such case, you can just count the frequency of the edges and put it in the adjacency matrix. So basically, you can think of any system as a network, whether email network, the people you like send mails to, right? Facebook friendships, citation, collaboration, mobile phone calls, front-end interaction, and stuff like that. But now we are going to focus on the web as a graph, and I will just tell the story of Google, what makes Google to become Google when they were nothing, right? I mean, Google did exist at some point in time. We have stuff like Yahoo search and basically, but Google implemented something that made them to kind of stand out and lead as far as search engine is concerned. So the web can be thought of as a graph or as a network. So the web can be thought of as a laboratory for understanding the pulse of humanity, right? Basically, we can see the web from that angle. So if the web is a graph, what are the nodes and what are the edges? The nodes can be the websites, or a web page, and then the edges can be an hyperlink. So if there's an hyperlink, if there's an hyperlink between um two web page, we create an edge between those two web pages. And the network for a like the network representation of the web is directed, right? There's a direction. If web page A connects, if there's an hyperlink that takes you from web page A to web page B, there's a form of direction in that edge. But it doesn't mean that web page B can take it back to web page A, right? So the web can be thought of as a directed graph, basically. So basically, you have this web page. So for example, there's an hyperlink that takes you to this other website, and stuff like that. So each web page can be seen as a node, while the if there's a hyperlink between two web pages, we create an edge between them. So basically, these guys, some skins, borders, and like they basically try to understand the web as far back as 1999. They basically created over 203 million web pages, and they realized that there are over 1.5 billion connections between them, right? So let's look at it in more details. Like I said, each node is like a web page. You get a connection between web pages, we create an edge. So it's a directed um, graph, right? But then I think it would be nice to describe something called SCC, which is a strongly connected graph. A graph is strongly connected if you start from any node and you can reach every other node. For example, if I start from node A, I can get to node B, I can get to node C, I can get to node D, I can get to node E. If I start at node E, I can get to A, I can get to B by following A and finally arriving at B. I can get to C by following A and finally arriving at C. So basically, everything is connected. You can actually find some paths that takes you from one node to any other node in the network. Such kind of network is called a strongly connected network. But if you can't reach every other node from every node in network, we call it a directed acyclic graph. DAG. I think most of you that have done big data tools, that have used big data tools like PySpark, you know that it creates DAGs, right, to represent the transformation, basically. So what is a DAG? For example, even though I can reach um, from node A, I can reach C and D, but I can't get to node B. There's a direction. I can't go against, I can't move. Remember, we are moving a directed graph. You must follow the direction, right? So I can't get to node B from node A because there's no way I can get to B somehow, right? Also, from E, I can get to C, I can get to D. But if there's at least any two nodes that aren't connected or there's no path between them, we call it a directed acyclic graph, basically. So, right. And one thing is that if you have a complex network, we can actually reduce it to uh, to connections between SCC, right? Remember, SCC is strongly connected component. You can reduce all network to maybe you see that, for example, if you have this big network, it can be reduced to 4 SCCs. For example, there's a big community here where everybody can reach everybody, while there's another one here just on its own. There's another lone community and another lone community. So if I reduce this to 4 nodes where if I consider this entire community as a single node, you will see that we then have 4 nodes, 1, 2, 3, and 4. And if you look at these 4 nodes from the eye level, you then see that it's a DAG, right? It's a directed acyclic graph, because if I start from this community and I leave this community, I can never get back to this community again. But if I leave this bunch of websites that are connected together, there's no how I can go back to it, right? So we can think of a network as a DAG of SCCs, right? All of this would make sense to why do we care about SCC and DAG? I think you get to understand that very soon. Yeah, so basically, I mean, this is just basically what I just explained, DAG and FCC and stuff like that. So let's go back to the web being a network, right? Okay, so these guys, like, they kind of try to understand how the internet is connected as far back as 1999. And they realize that there is a single giant SCC. Like, there are a lot of, you can basically get to every other website in the world if you keep following an hyperlink, right? Not all get the same, but it's a big SCC, right? Why is that so? If you were to have 2 communities of web page, the chances that there's a link that connects you from one community to the other community is kind of high. And there's also a chance that there's also a link that connects you from this community back to the other community. So therefore, if there's a connection between these two, you can merge these two to form one big, strongly connected component, right? So that's why there is a one big connected component. So they thought that is going to be a one big connected component. That is a heuristic argument, right? But I think I went back. But they saw that there's a both side structure, right? So notice why they were pointing to their both sides here. So when they plotted the network of the internet in 1999, they discovered this both side structure just appear. So there's a giant connected component where we have a lot of websites that if you keep following the hyperlink, you can basically get to every other website, right? There's a very strong connection among those central SEC, right? And then there is another set of community of websites that are a community on their own. They're also connected amongst themselves, but there are few links that you can follow that will take you that will take you outside of this community to the SEC, and you can never get back again. So those are called the giant in websites. Then if you follow those few links that takes you to the SCC from the giant in website, this website are also connected among themselves. There are also some few links that will take you out of this SCC to another community, such that you can never get back to the SCC again. Those are called the giant out websites, right? And then there are some few dangerous communities from the in that you can also enter those community, but you are not entering the SCC. You are entering another smaller community that you can never get back to the in again. So those are the dangerous community, right? Similarly, there are other dangerous community that can take you to to this giant out community. Those are also dangerous. Then there's a tube community that connects from in by bypassing this SCC to the apps community. So basically, you just see this both side structure of the graph, right? Of the internet. It consisted of 203 million web pages and 1.5 billion hyperlinks as of year 2000, right? Then there are some disconnected components that aren't even part of this entire both side. But this both side structure is very interesting. Like, they were so surprised. Wow, okay, cool. Then researchers at Stanford started researching on how to organize websites, right? Previously, Yahoo just did a humanly curated website. If you search that, they just have this big directory of website. You just have to look at the website yourself, what you kind of search, and everything that matches that search just come to you. But that is a bad idea. Why not just try to apply information retrieval algorithms, right? Look for maybe you calculate the similarity between a search query and the content of website to to kind of give a similarity metric. If you also do that, which is what Google, when they came on board, that's what they did. But here's a problem. If I search I'm on your internship on Google, there are actually over hundreds and thousands of websites that matches my query. But the question is, what are those websites that should appear to the uh, user? Like, what are those top 20 or top 100 websites? They should be the most important website. They should be the trusted website because there are a lot of mirror websites and fake websites. People just try to clone stuff and attract people to their website and infest them with virus or, and stuff like that. So Google actually came on board and we're thinking of a way to rank websites, right? It's not just enough to find similar websites, right? So let's say to my search query, there are 5,000 websites that are similar to my search query. How do we rank them to appear, right? So we need a ranking system. So yeah, basically that's what I just explained. And then what did Google do, right? So Larry Page and Sergey Brin, they started thinking about like giving some kind of importance measure to websites. Like, how can we give some measure of importance to website? What makes a website A to be more important than website B? They said all websites are not equally important, so they need to come up with a way to give a measure of importance to different websites. And they came up with the PageRank algorithm named after Larry Page, who is one of the co-founders of Google. They were actually PhD students in Stanford back in the 90s when they came up. So PageRank algorithm is also called the Google algorithm. It's what makes Google today. Uh, so a page is important if it has many links, right? But the big question is, do we care about the links that are coming into the page or links that are taking you out from that page, right? So they said, well, we can think of the link that takes you into a page as a vote, right? If I have a website and a lot of links are taking you to my website, that means my website is actually important, right? So we can think of in links. In fact, we have two types of links. We have in links and out links, right? The links that takes you from a node are the out links. The link that takes you into a node are the in links, right? So we can think of in links as votes, right? If a website has many in links, it's as though many other websites are voting that it is an important website, right? So basically, yeah. But then, are all links equal? Next question. Okay, so they started thinking of, for example, if you look at this website J, these two websites takes you into this website. So we can think that, should we just take the raw count and say, okay, because there are two links and all, then it has an importance of two? No, because even though there are two links that comes in, we need a conservation of importance, right? The number of importance that comes into a website should be the number of importance that takes you out of that website. We want to think of a flow system. We have two in links, but we have three out links from node J. That is not conserved. So we need to think of a importance matrix. So let's call that importance matrix R, right? So importance matrix. So the importance of website I is arrow of I, then K is arrow K, J is arrow J, right? We can think of, instead of us to just count the number of in link, we can think of that the importance of node J is the sum of the importance of the in links, right? So the importance of J is that of I plus that of K. But then why didn't we just do arrow I plus arrow K? Because I also has some arts links. So we say if the importance of I is arrow I and arrow has three arts links, so we divide it by three. So for every website that you get to from I, it's as though I is giving you a third of its importance, right? Because it has three arts. So that's why we took so that's how we normalize by the apps links here, basically. But then if we have this kind of formulation, the goal is to find ROI, ROK, and ROG so that we know the importance of each link. But this is a recursive question, right? Because we want to know ROI, but we want to know ROG, but ROG also depends on ROI and ROK. So how do we solve that? So it's a recursive problem. So let's think about it
Hi,
again.
Jeremy.
Yeah.
Jeremy, can you hear me?
Yeah.
Yeah, sorry for cutting you short. A quick announcement for the audience. Okay,
Okay.
so before Jeremy moves towards the end of his slides, please note that the second attendance form will be dropping on Zoom and YouTube for show names starting with letter A to M. Again, starting from letter A to M. So just check YouTube and Zoom for that. And the secret code is Apache, all lowercase. You have 5 minutes to fill it up. Okay, Jeremy, you can continue. Thank you.
All right. Yeah. Thank you. Yeah. So yeah, we see that node B is very important, right? That's why we make it bigger, right? So if we size the node by that importance, it's very important. Why? Because we have a lot of nodes pointing to node B. But node C doesn't have a lot of nodes pointing to it, but yet it is highly important. Why? Because this highly important node B points to node C. So if you have a loan website that is being linked to by very important website, that website should equally be important too, right? So we have this kind of formulation and stuff like that. And then if we have this stuff and you present the flow equation, you're going to have this, but it's a problem. You cannot find the value of arrow Y, arrow A, and arrow M because of the rank of these equations, right? So we have more number of variables than number of equations. So we cannot solve it algebraically, right? So how are we going to find the values of the importance, right? So Google came up with something called, so we just kind of do a multi-color process, like it's more like a Markov chain, right? Where we start with some random arrow. So this arrow is a vector. So if you have 10 nodes in your graph, arrow is going to be a vector of 10 values. So the goal is to find the importance of those 10 nodes. So we initialize, it's just like gradient descent, right? For your weight in a neural network, you start with some initial value and then you begin to update it, right, based on the loss, right? So basically, we initialize the rank of all the, what's it called, the page rank of all nodes with some R, right? And then we create a matrix called M, right? So this matrix is called stochastic adjacency matrix, just the adjacency matrix, but we should ensure that the sum of the column is equal to 1, right? And then if we have this matrix, basically, if we use it to multiply arrow, we get a new arrow, right? If you keep doing this process, you use this new arrow to multiply M again, and you keep multiplying just like, like a Markov chain process, right? We see that after some time, you're going to converge. The arrow vector is not going to be changing much again, right? It's going to converge to the sum true value. So that was Google's solution to finding the rank of all web pages, right? So, and then what is the intuition behind that, right? We can think of it as a random software. If after you've run your algorithm, your page rank algorithm for like 100 iterations and the arrow have converged to some value, how do you interpret the final rank of all web or site? We can think of it as the probability of a random software who is randomly clicking on any hyperlinks in any website. You just go to a website, if there's any hyperlink, just randomly follow any hyperlink. You go to the next website, randomly follow any hyperlink, just randomly surfing the web, right? If website J has an importance of arrow J, right? The intuition behind arrow J is the probability of a random software landing on that website. So that's just basically it, right? So and I think that makes a lot of sense, right? So this is just basically the multi-color process I have explained. But there are two problems. Number one is called the spider trap. Spider trap occurs when there's a website that links to their self, right? They have a self link. So if the random software is following our website and it gets to such kind of website that only links to their self, the random software is going to be stuck in that website and it can't go to any other website again. So if you run your Monte Carlo algorithm where there are some website that have some safe link, you will see that after the first iteration, let's say this is your value, after the next iteration, the arrow is not going to change. It's not going to be stuck, right? Because it will look as though like nothing is changing quickly. So every other thing will become zero and only this guy will just take all the importance. So that's the spider trap, right? The next problem is called the dead end problem, where you have a link from website A to website B, but there's no hyperlink from website B to any other website in this world. So yeah, it's called the dead end. So when the random software gets to such website, it's going to be stuck for life. Like it can't leave. The whole algorithm is going to fail. Right? The algorithm is not going to converge. So we can say website B, we absorb all the importance of website A, and then that's all. So those are the true problems, right? So we can think of these tendencies as dead ends, right? Because in this both side network of the entire web, if you get to these tendencies, you are not going to get back to these other guys again. So those are dead ends, basically, right? Okay. So what is Google's solution? So Google just said, okay, imagine if our network was initially this, and we have these guys that have spider trap where they just link to themselves. You just create some some fake hyperlink between every node and themselves. So let's assume all nodes can reach every other node. Every website can reach any other website with a probability of 1 minus b, where beta is so if the random software is surfing the websites in the world, right? So let's assume a value of beta to be the probability of the website randomly following the actual links in the website. Then 1 minus beta is the probability of the website jumping. So if the random software follows from A to Y and it comes from Y to A and it goes to B, it has two options. We are going to create a fake link from M here to maybe to jump to Y or to A, even though that link does not exist. So the random software has two options in this spider trap. Either it follows this fake link with the probability of 1 minus beta, or it follows this one with the probability of beta. So sometimes it will follow this one, it will be stuck. But after some time, this probability of 1 minus beta will kick in and is going to shoot out from this spider trap. So that was basically Google's solution to spider trap. Right? So dead end, they used teleporting basically, right? So it's just similar to the other solution, right? We just create a like we can say if we move to A to Y, Y to A, and A to M, since there are no links, we create fake links to connect M to every other node. So you must leave M like 100% sure with a probability of 1. You can leave M to any other node. Like there's an equal probability of leaving M to every other node. So that was basically their solution. And after they did that, okay, so like this is just me, right? One of the stuff I did in school here. I just created a network of the NSAS trend in 2020, right? Yeah, and then I ranked each user. So basically, each node here is a user on Twitter. Then there's a connection between them if they mention. So first of all, I first of all extracted all the answers, all the tweets pertaining to answers for a particular day, right? So a user is a node, right? If a user mentioned another user in this other, so there will be a connection between both of them, right? And then I kind of ranked each user based on their page rank value, and you can see that we can detect the influencers of that trend, the people that drive that trend, and yeah, you can see users like Aisha and some other top users here, like this guy who's also the main influencer of that trend, right? People like this guy, people like macaroni. So like this is just one of the nice stuff you can use PageRank to do. You can use it to rank your network and the different nodes in your network and find some useful insights. Yeah. Okay. Can't stop here. I don't know. Okay, somehow my slide can move to the next. I'll just go there manually. Okay. Yeah. So this is Larry Page and Green and David Green when they implemented the PageRank
I met 25-year-olds
in 1998, and they got their first investor. Like the guy invested some hundreds of thousands of dollars, and they went to Burger King to celebrate.
PhD students Sergey Brin and Larry Page, who have started an internet search company called Google. The company's right here in Larry and Sergey's room in the William Gates building at Stanford. The Google boys, as part of their PhDs, created a search engine, software that finds useful information on your behalf on the internet. It does what Yahoo or Excite do, but Larry and Sergey believed it did it much better and believed they could form a company based on it.
We talked to a couple of different people, like 4 people or something like that. And all the people we talked to were willing to give us money. We met this guy. He quickly, he took a quick look at our search engine. We chatted with him a little bit. We started talking about, well, he said, oh, I'd be interested in investing. So he said, I don't want you guys to have to, take too low a valuation or to have to worry too much about these money things right now. Why don't I just write you a check? So he went back to his car, came back with his checkbook, and he wrote us a check for $100,000.
The Google boys, meanwhile, are valued at $10 million and told me they were off to Burger King to celebrate.
Yeah, so that's the story of Larry Page. After they came up with the PageRank algorithm, man, we just went to Burger King to celebrate. But yeah, we are today. The world has evolved. Yeah, just a nice thing you can use network to do, right? So basically, it's a nice story. And then lastly, I will just talk about that you can even do more with network. For example, you can think of creating, right? Maybe you are running machine learning model, and we know that in machine learning, your data needs to be kind of structured, right? You have basically your data should be rectangular, right? Not irregular stuff. Unless you're working with some unstructured data, and even at that, you have to tag to make sure it is rectangular. So you have this kind of connection of network. How can you transform it to a kind of embedding space, right? You can use neural network. So if you have this network, you can take the adjacency matrix, right, and kind of learn some latent representation of this network, and then you feed that into your machine learning model, or you can use it as a feature, maybe to detect anomaly, to cluster stuff, and to link prediction, and maybe to do community detection kind of stuff. So it's very, very important. But the goal should be that if two nodes in the original network, like U and V, if they are similar, you need to define a similarity metric. If they are similar in the original network, if you transform them to your embedding space, they should also be similar according to some embedding similarity metric, right? So that's just one of the things you can do, right? And if you do the random walk algorithm, you can see the similarity. Like if 2 nodes are similar in the original space, right, we can use the similarity matrix to be the probability of getting to node U if you start from of getting to node V if you start from node U, right? So if this is node U and node V, if the random software starts working, we can say the similarity between node U and V is the probability of the random software landing at node V if you start from node U. And then we can use that as a similarity metric and kind of transform this from a network space to an embedded space where we have 2 vectors. And then from there, we can do things like recommendation and just some nice, interesting stuff. So some Python packages you can use for network analysis. The most popular one is Network X. I think it's very, very powerful. We have Network Sheets, we have iGraph and Graph tools. So thank you. Yeah. Questions?
Yeah, thank you, Jeremy, for that wonderful session. Thank you for enlightening us with all that. Your insights have been super helpful, and I'm sure everyone here, including me, has learned a lot from what you've shared. Okay, so before our speaker takes some of your questions, please note that the second attendance for short names M to Z will be dropping now, and the secret code is Apache, all lowercase. So remember that the form also will close in the next 5 minutes, so you can check YouTube and Zoom for the new form. And now to our questions. Remember to post your questions and comment on slido.com using the event code 32for1860. Again, remember to post your question and comment on slido.com using the event code 3241860, and they will be promptly attended to. Okay, we have one question from YouTube. So it's from Bemi. The question is, please, does this topic fall under the scope of artificial intelligence?
Yeah, sure. I mean, that's what you're doing. You are learning stuff. I think I've done a kind of with more year on artificial intelligence, basically, right? So basically, all of those intelligence that are demonstrated by agents, by that such that tasks that human being already ordinarily could not do, right? So, and the other data science, this falls other data science. So data science is right those set of AI, uh, those set of intelligence that can be gotten from using data, basically, right? So, and then this is an intelligence, right? You have a network, a complex interaction system, and then you want to like look for some kind of interesting communities. Or I mean, I gave a lot of use cases of network, right? So basically what Facebook and Twitter and all of these guys used to recommend people to use, what Google used to rank websites, it was the government used to track people of fraud and contact tracing in the pandemic. Airline use it to plan their traffic and stuff like that. Yeah. So it's first order artificial intelligence. You're using data and you can do more with it. You can move all the way to deep learning by, creating embeddings of your network. And it's just not enough to use maybe like you have some data and each observation attribute of a particular user of Facebook and or on Twitter, and then you want to use that to predict something, right? It's also nice to document your data with some kind of interaction, right? This users also like each row also interacts among themselves, right? So you can embed your network space to an embedded space and augment that to your data to kind of give some boosting power to your model, basically. And I think some companies do that. Yeah, so it's part of artificial intelligence. Yeah.
Thank you for that, Jeremy. All right, we have another question here from YouTube. Can you give a little explanation of directed link in terms of a conference call as opposed to the example you gave was
Well, I mean,
just a single link call? Okay,
is
let
there
me
in,
just go back to the question again. The
okay.
question is, can you give a little explanation of directed link in terms of a conference call as opposed to the example you gave? I think it was just a single link call. Yeah.
Okay, I believe the person is trying to say, I don't know if I'm right, but I believe the question is in my example, in directed link, we have a like link between two nodes and there's a direction from node A to node B. So those are just two nodes, right? And I also said that we can model interaction of people on phone calls as a directed graph, right? Where if I call you, there'll be a link from me to you. So the person is asking, what if we have conference call? We have a lot of people, right? They are all on the same call, right? So I think in that case, it depends. There's no one fit solution on that. It depends on the problem you want to solve, right? If you just want to solve and look for those people that are initiating conversation, like those people that are doing the dialing, they are dialing people to like speak with them on phone calls. In that case, if I am the one that started a conference call, then a link should start for me to every other person that are present in that conference call. Yeah, the link should originate from me to every other person, to be pointed from me to every other person. Yeah.
Yeah, thank you for that, Jeremy. I'm still waiting to see if any questions will come in. So it's question time, guys. So you can go to slido.com and put in your questions there, or on YouTube you can drop your questions and someone will pick it up and send it across. So let's just wait like 1 more minute. Or you can drop your question in the in-chat box. Okay, I just saw one coming. So this person is anonymous. Person is asking, please, as a budding data analyst, can you give an example of how I can apply this network analysis in my work?
Okay, it depends on your work. I don't know what your work is, but I think I
I think
gave.
the person is trying to say he or she is a data analyst.
Yeah, but data
Yeah,
analyst
can
can
you give
solve.
an example?
It depends on your domain. I mean, it does analyst can work
Okay, okay.
in like if you are working in finance, what's the problem you are trying to solve with data? So I think I need to know that problem. But I think Generally, I can give you some, like, I think I'll just go back to the different examples I gave, maybe from there, and because unless you want to speak with me privately, but just to answer this question, like why everyone is in this call, like these are some of the things they use it to solve. For example, Facebook social graph, you can do Facebook recommendation, but you want to recommend people that are connected. If I'm connected to you in Facebook network and you are connected to some other person, Facebook wants to recommend these guys to me too, right? So it maybe can use it to boost your recommender engine. Maybe for water supply, right? Especially like if you have connection of like different water sources and the pipe is connecting or gas supply, right? You want to know the most important station, right? Maybe that in fact there are some things called centrality measure, right? We have the betweenness, we have the shortest paths, like calculating the shortest path between node A and node B, right? So maybe they want to know the most important station, so that station should not break down. Maybe if there's a pipe that is passed, like if there's a pipe that connects that takes like some stuff, maybe water or gas from community A to community B, and that pipe is very important in that network. You want to make sure it is highly maintained because if that network, if that pipe breaks down, another community in your network are going to be disconnected from the supply, right? So you can actually do that to identify those most important one and maybe try to advise your company to build more and know when to build more so that we don't depend on only one. I mean, in traffic, for example, like uh, if you working for an airline and you build the graph of all the connections of all the different locations, and then you may maybe from that graph you can analyze that okay, if we are always living from here to there, but there is another um airline that lives from here, let's say from here to there. Why not just we create an airline that goes in between? Because we know that people in this region are also likely to get here. So let's just bridge that gap or something like that. Epidemic, contact tracing, right? You want to trace a new if an infected person just came into the country and then you want to create a graph of the movement of that person and then try to quarantine everybody that person came across so that they don't spread the disease. So you can look at the graph of that person and try to look at the people the person came across with. And on Twitter also you can identify communities on Twitter. Remember I said the web is a laboratory. Everything that goes on the internet, it just makes us understand the pulse of humanity. Like people, governments use it, like politicians, like to identify influencers of a particular trend and maybe ask them to promote their ideas on those social media and stuff like that. So basically, fraud detection, you can trace the movement of money in a graph, right? So it's not something you can do manually, right? This guy moves a lot of money. I mean, you can identify those things using graph analysis. And I just give you this beautiful example of the Zachary Club. How you can even predict, like you see employees interaction in your company and you notice that communities are being formed. You may want to understand as a human resource analyst the fact that communities are forming doesn't mean that they are bad. They may be useful communities, but you may just want to interview people individually to see those communities are actually have ideologies that are contrary to the other communities so that they don't split in the future or create a toxic work environment. So they are just unlimited use cases. So and it is specific to your domain. Yeah.
Yeah, thank you for that, Jeremy. The insight was the different applications it's actually clear. I have another question. How do we get to know which network analysis or algorithm to use for a specific problem? So is there a library where we have already prepared analysis that can be used for specific purposes?
Yeah, there's Network X, which is what I use. I mean, I showed you the way I trace influencers of the NSAS protest on Twitter in 2020. I use Network X. So Network X has all of these page rank. Network X will just calculate the page rank score for you automatically, right? You don't need to um, implement that yourself. So Network S it can also visualize the network for you, and you can look up there. They have a very nice documentation online. You can look it up and just learn something new for yourself and use it to augment your current stuff. Yeah.
Okay, thank you, Jeremy. Can you explain the concept of ranking?
The
Likely
concept of
response when, hold on, it's not complete. Sorry, let me go over it again. Can you explain the concept of ranking likely responses when training a bot using retrieval approach for the best response specialists?
you are training a bot. I
Can
want
you
to.
explain the concepts? Okay, yeah, go on, please.
Yeah, you are training a bot and you want to rank the responses, right? So, I mean, it depends on your problem again. If you are, I mean, I believe you are seeing the training phase, so you have data sets and all. So, I mean, like I said, you have your similarity like metric between query and your source of truth, right? So the possible responses, of course, you can just do the normal similarity and look for the most similar one. But as far as training bot is concerned, first of all, I don't think every problem you need to use network to solve it, because network, they need to be some kind of complex interaction between entity. I don't see for a typical bot training, I don't see any interaction, because the idea of when you should use network is if you have entities that have interactions between them. You are working with users on Facebook, for example. You cannot deny that there are interactions between users, right? So rather than training, so when you want to look for, when you want to recommend, you see that there are interaction between users. So you may want to apply network analysis. But for bots, you are training it for responses, and your data set, each response, can you really build a network of the different responses? Are there some connection between responses? I don't think so. So I think it may not be that like applicable to your case unless I fully understand your case. Once you can create a network, fine, then you can apply network analysis. Are there some nodes that are connected to one another? That's the question you should ask them. But let me assume then if that is true, then you basically use stuff like PageRank to rank the responses, right? Because we have multiple responses, right? Yeah.
Thank you for that. I have another question. I think I'll just refresh it. So this person is asking, he or she is a fresher about to get into data science field. So how many years of experience should the person have before he or she can get a data science job?
Uh, I don't think there's a direct answer to that because there are a lot of factors. I think if you can also watch my previous video on Amway, I think I also talked about this. There are a lot of factors from your connection to your skill, to the availability of job, to your CV, to your, I mean, the way you job hunt and stuff like that. I don't think there's one, but I think you have just one job, right? Job hunting itself is a job, and your job as a beginner is to improve your skills as much as you can, right? So it depends on you, it depends on your learning curve, it depends on on the time you spend into preparing yourself. If you spend 10 years preparing yourself, it may take you 10 years to get a very good first entry level job. If you prepare yourself very well within a short time, you may shorten the time for yourself. But I would advise you, if on an average, let's say an average person with an average learning rates and stuff like that. So I think like I would just speak about the things you should focus on, right? Yeah, but I think on an average, like you should just start focusing on uh your very first year. If you spend 8 hours a week or 10 hours a week, I think after your first year of learning stuff like the basis of data science and stuff like that, you may want to start looking for internship after your first year while you are still learning, right? I think people after their first year, they just want to get into the full-time job by fire by force. If it comes to you, fine, you accept it, and then you learn in the process. Right? But I'm always someone that always emphasize preparation, right? If you give me 10 days to cut down in fuel, I'll use 9 days to prepare, right? So, and you can also learn on the job actually. So it's not that job hunting is bad, but I just feel like after your first year, if you do 10 hours a week, you should be up for an internship. And then while you are doing the internship, like a year internship, and you are also learning the process and you're also learning outside of what you are doing too, so that you'll not be left behind in the industry. I think after like 2 to 3 years or 2 years, cumulatively, I think you should be good. So like get your first job because your internship should have gained ample experience, right? Because interviewers also care about your experience too, right? They want to see what you have done, and an internship is one great way to create experience for yourself. Yeah.
Thank you for that. Okay, the audience wants to know how they can connect with you on LinkedIn.
Yeah. Just search my name, Jolami. I think I really put that. Yeah. Mine. Yeah, Jolami to sound me on LinkedIn, and yeah, you're gonna see me there. Yeah, you can connect with me on LinkedIn on Twitter. All right, that's X. Just search my name, my full name. So this, I think you will most likely see my LinkedIn page as the first one. You see my Twitter and some other stuff. Yeah, my and some of my articles and stuff like that. Yeah, but basically, just search my like yeah, Jolami to sound. Yeah, you're gonna see it's there. Yeah, basically. Jolami to sound me like linkedin.com/injolami to sound me.com. Yeah.
All right. So you have another
Maybe I'll drop
question. How
maybe I drop this in the chat box. Yeah. You can read the question, sorry. I'm sorry.
okay. Yeah, that's fine. How does the increase in bots on social media affect network graph ranking algorithms? How will network graph differentiate bots and human post ranking, especially on social media?
Yeah, I mean, one thing, and that's a very good question, and because one thing we both is that they are also entities, they are also nodes, and they are also interacting with people, right? But one way, of course, they are going to disrupt the whole pulse of humanity that we're trying to learn from social media, right? Because we have these fake humans just trying to interfere with what we are actually trying to analyze as data scientists. And first thing is to identify them, right? We need to identify these bots and maybe exclude them from your analysis. If your problem is about understanding the interaction amongst real human beings, right? You want to extract them, but you also want to study the interaction between bots. I mean, that's another problem to solve. But the first task is to identify them. And I think one way to identify them is that one thing about bots is that they kind of their rate of tweeting or interaction is kind of way higher than that of or human. Maybe you can create a network and you see those web nodes that have a lot of tweets within a short time or something like that. Or they interact at odd hours of the day, right? Maybe 12 a.m. You create a network of between 12 a.m. to 6 a.m. and you still see a lot of interaction from some certain users. Then you may want to start narrowing your analysis of those users and see what they can, and then maybe they are bots or something. Yeah. And then maybe their number of followers, a few followers, but a lot of interactions created within a short time. Like they join the social media platform within a short time, but they have a lot of interactions, basically. Yeah. Yeah.
Okay. All right. Thank you for that. I think that's all the questions we have. All right. So as yeah, that's all the questions we have. I don't think we have any other questions. Okay, cool. All right. As today's webinar comes to an end, we officially wrap it up. Big thanks to Juloni for sharing his insights and thoughts so generously. Every second we've spent here has been super informative. To our awesome interns and everyone who joined, I'm sure you've picked up some really useful tips and know-how from today's talk. Special thanks to the hardworking Harmony team and everyone who pitched in to this webinar. a success. Have an awesome weekend until next time. Take care. Bye, everyone.
Bye.
Hi, Jeremy. Please, can you please help us end the meet? You are the host. Thank you.
Yeah, I was wondering who to assign it to so I can leave this meeting. I was just looking for. Okay, so
Okay, you can
I
assign
can
it back to me, or you
you.
can
Yeah,
just
so
end it first. Yeah.
okay, I think since I can, yeah, I think I'll just send it. Yeah. All right, thank you. Yeah.